Hello, so today we're going to start with um, linear algebra basically. And how does linear algebra start? We will start with the basic topic of, wait a second, basic topic of, you can say, vectors. So, vectors is where we start mm, linear algebra. So simply in a simple term we can say a vector will be a list of numbers basically. So which will give you a magnitude, which will also give a direction. Um, like for example, if I say I want to go from A to B, right? So you might say go 3 kilometers. So 3 kilometers can be in this direction, in any direction, right? So let me define a direction to be, let's say 5, right? So um, so vector becomes, this vector will become 3, 5 for example. Again, this is some bullshit notation I am using. And so you have a list of numbers and each number will denote something in a space. Let's just think something like this. So for example, let's say you have height, weight, marks. So this will become, let's say height is 161, weight is let's say 52, marks is 100 marks. So this is a vector. Okay. So so basically it's just n numbers. Let's say this is 3, right? So it will be 3 numbers that each of which define something in some aspect, let's say. Okay. So this is what we get from vectors. Okay. And um, even before even after understanding how a vector works, let's work with two-dimensional vectors for now. So two-dimensional, you can name something like a column vector. Let's say v1, v2. This is a column vector, and this, let this be a row vector. So this only has rows. So row vectors are having a single row. So 1 into some number of columns, and here it will be what, one column and many rows. So it will be some rows into 1. So whenever you write a vector, let's say r cross c, it is written as row cross c notation. Okay. So that is it. Now I think this basic idea of vector is done. So let's now work with a bit of addition. Okay. So how does vector addition work? Vector addition will of course only work when you are adding two vectors of the same dimension, right? Why? So let's say I have 2, 3 plus 1, 5. How do you even add this? There is no logic, right? So let's say even if you are mapping 2, what do you map 2 with? Right? So there is nothing to map with. Even though, let's say if you even write it as, let's say 1, 1 and 1, wait. Let's say name it as 2, 1. This will be what? This is 1, 1. This is 1, 2, right? Even if you add this, let's say even if you add this as 3, then where do you put this? What is this thing? So you cannot do this, right? So for addition, you need to have the matrices to be so vectors to be same. So basically it will be like v1, v2, and let's say I have w1, w2. So it has to be v1 plus w1 plus v2 plus w2. Simple. Addition is simple like this. Okay. Now we'll talk about scalar multiplication. So scalar multiplication is nothing but you're multiplying a scalar value with the vector. So let's say v1, v2. Logically, this is very simple. Just multiply it with every term. So c1, cv1, cv2. This is very logical. Again, I don't need to explain this in much detail. So yeah. Again, the order, since you know the addition is what do you call it? I forgot the commutative, right? Yeah. Since addition is commutative or means a plus b is equal to b plus a, in this case as well, this vector addition will also be commutative in that aspect, right? So now with the tools that I have given you for the first things, we will define something called linear combination. Linear combination. What is linear combination? Linear combination is simply this. So let's say I have a vector v and w. A linear combination of v and w will be something like, let's say, c, wait, cv, let me capital V, and dw, where c and d are scalar values. Scalar values means a single value of sorts, like 2, 3 or something like that. Okay. So this is what a linear combination means. So like this might be one linear combination. This will also be, let's say this can also be, let's say -1 for example, will be a linear combination. Okay. So, okay, how do I represent this? Like, how does it look like in my graphical form? Like, let's imagine this a bit. Okay, so let's say, let me define V as, let's say, 4, 2, and W as what? -1, 2. Let it be like this. Okay. So, let's plot this, right? So, that would be better. Like, 1, 2, 3, 4, -1, -2, 1, 2, -1, -2. Okay, so let's plot V. V will be what? 4, 2. So V will be something like this. Let's plot W. -1, 2. So it's something like this. Okay. Okay, this is V and W. So simply let's try to do the yeah, simply let's just try to make one linear combination, right? Let one linear combination be 2V plus W. Now let's do 2V minus W. That would be better. So what is 2V? For 2V, so what you have to do is that what scalar multiplication does in this is that it makes it that times of that. So it will be something like this. I'm not drawing till 8. So this becomes 8. This will become somewhere 4, let's say. Okay. And minus does what? It reverses the direction of that. So if this was W, minus will do this. Okay. So what is addition? Addition is something like this. Addition for vectors can happen in two ways. So let's say if there is a vector here, and let's say if there is a vector here, right? If the head of something is touching the tail, you just join this line, and this is the addition. If the other case happens, like where the tails and tails are touching each other, then it will be in the middle somewhere like here. Okay. How do I find this line? Simply push this vector here. So this vector comes to be here, and this, now using this you can find this very easily. Okay. This is a vector addition will work. And I showed you addition, subtraction, multiplication. You have seen all cases here. Okay. So again, 3-dimensional, maybe this is very easy to imagine, right? So let's say a 3-dimensional vector is 3, 1, 2. It's very easy to imagine. Just draw the 3 diagrams. Go here. Let's say 1, 2, 3. This is the 3. And 1 here. 2 here. So you draw this like this. go till this distance, this becomes the three-dimensional vector, something like this. Very bad at drawing though, but yeah. Okay, so now one must wonder these things. Let's say I have a vector u. What does cu mean? Cu, a linear combination where there is one vector, right? So what is u? U is a single value of vector, right? So let it be 2, for example. What will cu represent? C can be any value that belongs to R, a real number. So it takes every value like this. This is one single point. If I change the value of C, it will change points. So this becomes a line. So cu is a line. Okay. Now again, I don't wait, not like this. Okay, let u also be something like 2, 1, let's say, right? So if it's 2, 1 as well, it also becomes a directional vector or something like this. So even if I multiply any scalar, it will only move along this line, right? It cannot move up or down. So then it encompasses a line. So u, if u is any vector, it does not matter, it will always be a line, as simple as that. Okay, again a column vector is a main thing. Okay, I'm only talking about column vectors. What about cu plus dw? Now what happens? You have one vector, you have another vector. So this vector can encompass all the directions, right? So basically, if you understand one cu will encompass one single line, and dw is added somewhere, let's say here first, so you can put this line. So by rotating this dw, you can encompass this whole plane. Did you understand this? So basically, with respect to cu plus dw, we get a plane. Okay. So in the same way, if I do dw plus cu plus, let's say, ex, so this will give me what? This will give me one simple, some three-dimensional space, let's say a cube, I have no idea. So let's say a cube space, let's say, whatever the space is, okay. So let me give you some sums to understand this. So for example, I am giving two vectors 1, 1, 0 and 0, 1, 1. So yeah, it is given that the linear combinations of VC VW fill a plane. Okay, find that plane. First of all, find that plane. So if these fill that plane, what does that mean? This plus this will be the plane, right? So that is what? C plus D. This is my definition of the plane, right? Now they're telling me find a point which is not in the plane. So let's say 1, 4, 3. So 1 plus 4 is not equal to 3. So this is not in the plane. Okay. Okay. So next sum. V is given as 0, 1. W is given as 0. W is given as 0, 1. V is given as 1, 0. Tell me Okay, tell all the points CV. Okay, what are the points on CV? So again, this is very easy. This will be C0. Okay. So now this represents the whole line, right? So if I give you something like C greater than equal to 0, then what will it represent? Everything after 0. So this is a half line. Okay, half line. Again, if I do a CV plus DW, and I give C and D greater than equal to 0, what will that give? That will give a quarter plane. Why? Only this quadrant will be filled. If 1 is given, let's say C greater than 0, then maybe this will be filled. So this will be half a plane. So you have to be careful when these kind of sums are given. So if both conditions are true, then half a quadrant. If let's say there would be 3, so C, D, E greater than equal to 0, so that would become, let's say if this is a cube like this, so it will give you 1 octant, so 1 by 8 area only. Okay, so you have to remember this. Okay, so now next question is something like this. V is given as 2 minus 1, W is given as minus 1 2, B is given as 1 0. Finds such C and W. So it finds such C and D such the linear combination of V and W with respect to C and D equal to vector B. So what is the equation? C into 2 minus 1 plus D into minus 1 2 is equal to 1 0. Sorry, why did I give a by? So it's 1 0. So this becomes what? 2C plus, sorry, minus D, 2D minus C is equal to 1 0. So that becomes D is equal to C by 2. So 2C minus C by 2 is equal to 1. So 4C minus C is equal to 2. C is equal to 2 by 3. And D is equal to C by 2. So it's 1 by 3. I think this is the answer, right? So this is how you solve a similar sum like this. Okay. Let me find a very interesting sum. So this you can also have, you should be able to solve 3 for 3 as well. This is for 2, this you have to solve for 3 as well. So today this was the basic of vectors and how linear combinations work and how they work visually as well. So that's it. So if you want to solve some sums, so where to solve some sums, you have to get Gilbert Strang. So Gilbert Strang's book is there. You have to solve what do you call it, problem set 1.1, all the sums. So this is the questions to solve after this lecture basically. Okay, then we'll leave this for today till this much. We'll continue the next day.